Welcome back to Shooting Asteroids with Math. This is Part 2A. I'll get into that in a moment. In Part 1, I demonstrated the math necessary to shoot stationary targets. In Part 2, I will show you the math for hitting moving targets. I said this was Part 2A though. There are 3 different levels of precision we can use for shooting moving targets. In this video, I will show you the quickest and simplest one, which is probably good enough for most applications. This involves algebra and a small bit of trigonometry in the form of the law of cosines. In Part B, I will improve our precision a bit, still using algebra and trig. And in Part C, I will show you how to precisely calculate the aiming boundaries using the previous calculations and Newton's method. As I discussed in Part 1, there are 3 requirements for shooting targets: a target, an angle to aim, and the precision necessary to hit the target. As in Part 1, I will keep targeting very simple by selecting the closest asteroid to our satellite. The next requirement is the angle to aim. For that, we will be doing some math. Okay, before we do any math, we need to discuss the math that we'll be doing. Our goal is to find the angle to fire a bullet from the satellite that will hit the target. I set up this demo in Desmos to show how we'll get it done. Under satellite, I've set up the initial position as PS0, the initial velocity as VS0, and I've set up P-satellite as the position of the satellite for a given time. The target section has corresponding values: PT0, VT0, and P-target. Additionally, I set up some constants. S-bullet is the speed of the bullet relative to the gun, L-gun is the length of the gun, and theta gun is the angle that we'll be aiming the gun, but we'll do that later. Here's a circle I'm calling the bullet possibility circle. It appears around the satellite and shows where a bullet could be if it was fired at t=0. The bullet possibility circle is always centered on the current position of the satellite. This is to mimic how things work in space. From the perspective of the satellite, with no acceleration and ignoring details like recoil, which I do not model in my game, the satellite is not moving. The satellite must lead the target, and the bullet will fly straight out of the barrel of the gun. From our perspective, the satellite and bullet drift together at VS0, or the initial velocity of the satellite. In my game, the bullet appears at the end of the gun barrel at the time of firing. This means that the bullet possibility circle starts with a radius of L gun and increases with the rate of bullet speed. If we advance time to around 3.9 seconds, we can see that the bullet possibility circle crosses over the target. This means that 3.9-ish seconds is the first time we could hit the target. If we advance time further, we can see the other time it could hit the target for this setup. The first time is preferable because we'd hit the target sooner. Sticking with 3.9-ish seconds, we can then solve for the angle to hit the target. We need the relative position at time t for 3.9-ish seconds. To get this explicitly, I've set up p=pt0 minus ps0, and v=vt0 minus vs0. P and v are the relative position and velocity at time =0. We can then find pr, which is p plus tv. This is the relative position at time t. If we plug in our t, then we can take the arctan of pry and prx, and that's our angle to fire. Before we can use this angle, I need to add a gun. As you can see, there is now a beautiful line segment representing the gun, and the bullet, which is on the bullet possibility circle, in line with the gun barrel. Now, we just need to plug in the 1.15 radians we calculated and watch where the bullet goes. Set theta gun to our 1.15 radians that we calculated. So we'll go all the way back to 1.15 radians. We'll set it precisely here. And then we can go up to t, set it back to 0, and watch the bullet advance straight through the target. Okay, to recap, we found time t using the graph. We used it to calculate our angle. What we need to do now is figure out how to calculate t. That's what we'll do next on paper. Okay, as we discussed, our goal is to solve for t, and then we are going to use t to solve for theta. That is the angle that we need to aim to hit the target. I've set up our given variables here. We have p is equal to the position of the target at time 0 minus the position of the satellite at time 0, which is equal to, these are conveniences. I've set these up. Px is really the x portion of p I hat plus the y portion of p j hat, but these are just set up for convenience here. So we have v is equal to the velocity at time 0, or the velocity of the target at time 0 minus the velocity of the satellite at time 0, and similar vx plus vy. Then we have d. This is the distance between the target and the satellite at time t. And then we have r, which is the radius the bullet will be from the satellite at time t after it is fired. So what we need to do is we need to set r is equal to d. And then I'm going to ignore r for a little bit, and I'm going to write out d. So d is equal to, just as we set up here, we have p plus t times v and the magnitude of that. And the magnitude is the length, basically the length. In order to get the length, we can do the Pythagorean theorem. In order to do the Pythagorean theorem, we need to separate our x portion and our y portion of the vectors apart. And we can say, so we can say px plus t vx squared plus our py plus t vy squared, and that's all under a square root is equal to r. In order to get rid of that square root, we can square both sides. So we say r squared is equal to, same thing, px plus tvx squared plus py plus tvy squared. And then we need to do polynomial expansion on this. So I'm going to take this term first. So we say px squared plus 2t px vx plus vx squared, all of this, plus polynomial expansion of this term, py squared plus 2t py vy, this is looking very similar, vy squared. Okay, so then we can go ahead and gather our terms, and we say t squared, oh, excuse me, forgot those, t squareds. Okay, so t squared, those came from over here and here. Okay, so t squared times vx squared plus vy squared plus 2t times px vx plus py vy plus px squared plus py squared. I'm going to take a second to write some notes off to the side. We can say, we can write these in a couple different ways to make this a little bit more convenient. So we can say vx squared plus vy squared is equal to v dot v. It's also equal to magnitude of v squared, depending on how you like to write things. We'll start with this term because it's very similar. Px squared plus py squared is equal to p dot p, which is equal to the magnitude of p squared. And then our last term here is we have px vx plus py vy is equal to p dot v. So when we rewrite this, I will substitute in the dot forms just to make it a little cleaner. But first, I'm going to return to R, and I'm going to rewrite r over here, but remember we have our squared term. So we have our L gun plus t times the speed of the bullet. And all of this is squared. So we need to do polynomial expansion on this side. So we say L gun squared plus 2t L gun, speed of the bullet, plus t squared, speed of the bullet squared. And this is all equal to this. So what we can do is gather everything onto one side and rewrite everything. So we say 0 is equal to t squared times, remember we have vx plus vy is equal to v dot v. So we say v dot v minus our t squared term on this side, which is the speed of the bullet squared, plus t, I'm doing it this way, and I'm going to say 2 times, we have our pxvx plus pyvy is equal to p dot p, excuse me, it's equal to p dot v, p dot v minus our 2t term from this side, which is L gun, the speed of the bullet. And finally, we have our terms without t's, which we have px plus py is equal to p dot p minus L gun squared. So these are, we have a quadratic equation here, and we have t squared, this is our a, we have t, so this is our b, and we have nothing, we have no t, which this is our c. So for our quadratic equation, which I'll write up here, we have t is equal to negative b plus or minus the square root of b squared minus 4ac all over to a. So sorry, there was some noise in my house, so I need to re-record this section. Okay, so we're going to take our a, b, and c terms and plug them into our quadratic equation. This will give us two t's. The t's can be positive, they can be negative, or they can give us undefined or an imaginary number. What we're looking for is positive t's. And we pick the lowest positive t, and that is the earliest possible time that we can hit the target. Then what we do is we plug them into the PR equation from the last section, which is p plus tv, and we take that PR and we plug it into the arctangent, and that gives us the theta which we need to aim to hit the target. Okay, to summarize all that, we need to calculate ABC. Use those values to calculate the t values, where the bullet center will cross the target center. Select the smallest positive t, plug that t into our relative position equation, and finally calculate the aiming angle using arctan. I went ahead and added the math to my game, and set the precision to 0.1 radians for now. You can see that it successfully hits the target for our Desmos scenario. With lots of asteroids, you can see it already is doing much better against moving targets. However, given the static precision, it will still struggle to hit targets that are further away. That wraps up the aiming angle section. The next section is the precision. In order to determine the precision necessary to hit the target, we need the radius of the target and bullet. I've added arbitrary values for these. At the 3.9-ish seconds that we found earlier, the bullet possibility circle is right over the center position of the target. You can see, watching the bullet move, that there are other locations on the bullet possibility circle that would hit. The furthest location that would work is the distance between the bullet and the target, is where the distance between the target and the bullet is the sum of their radii. This is our boundary condition and the precision angle we're looking to calculate. The points of interest, the centers of the bullet, target, and satellite, form a triangle that you can see here. When we know the length of the sides, so we can use the law of cosines to find the angle we're looking for. For the law of cosines, we define a triangle to have sides lowercase a, b, and c, and angles capital A, B, and C. On the right, you can see the law of cosines solved for angle C. To use the law of cosines, we need to define our sides. On our triangle, I will call this A, this B, and this C. That means this will be our angle C, and that's what we're looking to calculate. Under precision, you can see I set up A is equal to L gun plus time times the speed of the bullet. This is the radius of the bullet possibility circle. B is equal to A because both of these sides have the same length. And C is equal to our bullet plus our target. We then plug those values into the law of cosines discussed on the last page. This is our angle. So I'll take away the precision, I'll take away the triangle and show the precision. You can see that this produces a range anywhere inside of which we could shoot and hit the target. To summarize the precision section, we need to use the law of cosines to solve for our precision angle. We plug in our values to find A, B, and C, which gives us the angle. If you want the full angular range, just multiply this by 2. That wraps up the precision section, which wraps up the math for Part 2A. Once again, thank you for watching. I hope you enjoyed the video. Please like and subscribe. I'll have Part 2B out soon.